Here are the four ways theorems can be stated in if-then statements. There's the statement, which is the form the theorems we just went over were given in. There's also the converse, the inverse, and the contrapositive. Let's take a look at the statement and the converse of one of the theorems we just went over.
Here's our statement in the good old if-then form. You know, if P, then Q. If two lines intersect, then they intersect at a unique point.
If we take our statement in if P then Q form and reverse it to if Q then P, this gives us the converse. The converse is, if two lines have a unique point in common, then they intersect.
So, that's the statement and its converse. Later on, we'll prove theorems by proving, step by step, the statement and its converse. We won't go over the inverse and the contrapositive now, because if the statement is true, the inverse is also logically true. Likewise, if the converse is true, the contrapositive is also logically true. This all seems more confusing than it really is. Just know that there are four ways to state theorems, and also that when a statement and its converse are true, all four statements are true.
When all four of the if-then statements, the statement, the converse, the inverse, and the contrapositive are true, they're especially strong. We can unite their forces to create a big superstatement.
This superstatement is known as the biconditional statement. A biconditional statement has the form P if and only if Q. So the biconditional of if two lines intersect, then they intersect at a unique point is two lines intersect if and only if they intersect at a unique point.
And when we say it and prove it, it means that all four variations of the theorem are true. As we prove theorems in the if and only if form, the biconditional form, we'll prove the statement and its converse. We won't need to prove the contrapositive and the inverse because they'll be true if the statement and converse are true.
All right, we'll get to more if and only if statements when we prove theorems later. Before we move on, let's make sure we've got the basics.
A postulate is a fundamental assumption that can't be proven, but we accept as true. A theorem is a statement that can be proven with postulates, definitions, and other information we'll talk about later. There are four different if-then statements: the statement, the converse, the inverse, and the contrapositive. We can form an if and only if statement when all of these are true. We'll prove the statement and the converse as we show the validity of theorems.
Part 2, Angles. Section A, Angles defined.
Okay, an angle is two rays that share the same endpoint. Let's take a look.
At point A, the angle is formed by rays AC and AT, which form the sides of the angle. They share endpoint A, which is the angle's vertex. Point S is an interior point because it's inside the angle, and point H is an exterior point because it's on the outside. This angle can be named four ways: angle A, angle CAT, angle TAC, or just angle 1. Notice that the vertex A is always listed in the middle of both the CAT and TAC notations.
Look at these two angles here, YAP and DOG. The measure of angle YAP is 60 degrees. We see that the measure of angle DOG is 60 degrees also. So as we said earlier, two angles that have equal measures are congruent. So the measure of angle YAP is equal to the measure of angle DOG, and angle YAP is congruent to angle DOG.
YAP and DOG are what we call acute angles. Acute angles measure less than 90 degrees.
A right angle measures exactly 90 degrees. We designate a right angle by putting a small square at the vertex of the angle. An obtuse angle measures more than 90, but less than 180 degrees. A straight angle measures exactly 180 degrees. Note that a straight angle looks just like a straight line. We told you geometry is mystical.
Now that we have single angles down, let's look at some pairs of angles that have special names.
First, adjacent angles. Adjacent angles are coplanar angles, you know, the kind that lie in the same plane. They have a common vertex and a common side. Since the adjacent angles are touching and not overlapping, they have no common interior points.
Next, let's look at complementary angles. Complementary angles are two angles whose measures add up to 90 degrees, like angles Y and O here. The measure of angle Y is 33 degrees, and the measure of angle O is 57 degrees. If we add the measures of angle Y and angle O together, we get 90 degrees, the measure of a right angle. So angles Y and O are complementary.
Supplementary angles are two angles whose measures add up to 180 degrees. Like angles D and A. The measure of angle D is 99 degrees, and the measure of angle A is 81 degrees. We add the measures of angle D and angle A together for a total of 180 degrees, which is the measure of a straight angle. So, angle D and angle A are supplementary.
Notice that complementary and supplementary angles do not need to be adjacent. It's all about their measures. They could be lying around just about anywhere, as long as their measures add up just right.
Next, vertical angles. Vertical angles are two angles that occur opposite each other when two lines intersect. When these two lines intersect, they form four angles. In this diagram, angles 1 and 2 are vertical angles. So are angles 3 and 4. The cool thing about vertical angles is that they're congruent. So if you know the measure of one, you also know the measure of the other.
For example, if we're given the measure of one of these angles, we could figure out the other three. Watch this. If angle 1 is 55 degrees, then angle 2 is also 55 degrees, because they're vertical angles. See that angles 1 and 3 are supplementary angles? Together, their measures will add up to 180 degrees. We know the measure of angle 1 is 55 degrees, so angle 3 measures 180 degrees minus 55 degrees, or 125 degrees. Angle 4 also measures 125 degrees because angles 3 and 4 are vertical angles. So we've got all four.
Vertical angles are really powerful tools that we'll use a lot when we get to proofs. But before we get to proofs, let's look at some other angle stuff.
An angle bisector is a ray that splits an angle smack dab in the middle, forming two congruent adjacent angles. Here, ray QR bisects angle SQT. Angle SQR is congruent to angle TQR. Note the curve symbol inside of each of the angles. If there's a slash in each one, then that means the angles are congruent.
And finally, perpendicular lines are intersecting lines that form right angles. Rays and segments can also be perpendicular. Here we have two perpendicular lines, L and M. So all four angles, D, O, G, and S, are right angles. When we write that two lines are perpendicular, we use a special symbol. L is perpendicular to M.
An angle is formed by two rays that share an endpoint. Adjacent angles are coplanar angles that share a common vertex and side. Complementary angles are two angles whose measures add up to 90 degrees. Supplementary angles are two angles whose measures add up to 180 degrees.
Vertical angles are congruent. An angle bisector is a ray that splits an angle smack dab in the middle. Perpendicular lines are two lines that form right angles where they intersect. And a proof is a series of logical steps that prove the truth of a theorem.
Parallel lines are two or more lines that are contained in a plane and never, ever touch.